many people here as well. So thank you all for coming to our second and last colloquium series, CASMA colloquium series for this semester. I promise that next fall, if COVID stays how it is now, or even better, we will have many more. I think that Dr. Templin have an
I was just going to say,
announcement
this
about
fall,
that.
we're going to have an EMS Pro seminar at this time every Friday, some of which will be the CASMA Colloquium. There'll be more announcement on that in the email coming soon. Hopefully, professors, students, all of us will have the chance to see research every week.
No, you're good. Thank you. I asked Professor Lisa Hoffman if she wanted a long or short introduction, and she told me a short. So all that I'm going to say is that, can I call you Lisa when I introduce it?
Yes, you may address me by my name. That's okay.
Good. Thank you.
Yeah.
Lisa, main area of research has been longitudinal data, but don't let that tease you. She has the most awesome notes that you can find about many things in her website, including things like measurement invariance and IFA, among many other things. So I will stop rambling around and let actual speaker to give her talk. Her title is Explanatory Latent Traits Models, a Tale of Two Stands. Thank you.
Thank you, sir. And thank you to all of you who are making time for this at the end of the semester on a Friday afternoon. Way to show some dedication. I really appreciate your support. As Ariel said, I probably am best known for longitudinal stuff, but what I have to talk about today has nothing to do with that. I will be honest, this talk is being recycled from talks that I have given on this topic in the past. So you'll see some older stuff, but I also couldn't resist adding a few new twists to it as well. The work that I'm going to talk about today is actually from my days as a graduate student at the University of Kansas. So way back when I was an undergraduate, I was a psychology major, and I really liked the research methods and stats classes that I was taking. And I asked the person when I went to talk about grad school opportunities with my instructor, whether I could go to grad school in psychology for just research methods and stats. And he said, no, that's not a thing. It was 1998. We didn't have the internet everywhere. I trusted what he said. Then I said, okay, well, what do I need to do? You need to pick a content area. And then you can keep taking the stats classes that you really want to take. Okay. So amongst all the classes I had as a psych major, I liked the cognitive psychology classes the best. I was interested in the confluence of working memory and attention and selective capabilities as they intersected with human factors, and I thought that kind of stuff was cool. And I ended up picking the University of Kansas to go to grad school because they had a program that was called experimental psychology, which was a cognitive track and a quantitative track, where the quantitative track was exclusively Susan Embretson. Many of you probably know her work in item response theory. So by quantitative, they meant measurement specifically, not all of quantitative stuff. But as it turned out, about a year after I started, the program split into two separate programs, and they said, you need to choose, and I said no, and I kept trying to do both of the things. And so the work that I'm presenting today is really a blending, or my attempt to blend those two worlds, what I learned in the process, and how I think the way that I've come to view quantitative methods as a series of interlocking pieces can be leveraged to make the work even better than it could otherwise be from just sticking in one paradigm. So what are those interlocking pieces, you ask? Hang on here, I gotta get to the right screen. Come on. No, my mouse is going crazy. I don't want this set up, thank you. Come on, there we go. The scroll wheel works. Legos. So for those of you with small children, you will recognize the picture on the left. Here is what the Legos look like on the carpet while they're piled everywhere after someone is done with them. But Legos are really cool because all by themselves, they're very simplistic little blocks. But you can put them together in amazing combinations to build some really cool stuff, just like this exhibit at the Mall of America. So the way that I've grown to appreciate this in cahoots with Jonathan here, we think of statistical methods, quantitative methods, as being a series of Legos. And if you understand the basic building blocks and you can figure out how to put them together in creative ways, you can do anything. So what the Legos are, number one, linear models. Linear models run the world. In order to do fancy things with linear models, though, we need better methods of estimation. In order to predict different kinds of outcomes, we need link functions. And then the fourth one is interesting because I have it labeled as number 4, but yet there's all the words. Yeah, question?
People in Zoom can see you, not the screen.
That would be because I didn't share it yet, because I'm apparently at the end of my semester as well. Thank you, Zoomers. And I need to turn on the transcript probably too, that will help. And then quickly hide it from myself so that I don't have to see the terrible translations of my words.
Fish sticks.
Yeah, fish sticks, or sad earth weight, as I heard. It's sad earth weight. Okay, and then I need to hide this, and now we're good. Okay, Zoomers, are we good now?
Yes.
Yes? Okay,
Yes.
cool. All right. Divided attention at work. See, this is what makes it interesting. So anywho, number 4 here is listed as one thing, but it actually goes by a lot of different names, and that's part of the confusion as to what things are the same and what things are not the same. So we've listed random effects and latent variables otherwise known as latent traits, latent factors, latent constructs, true score, theta, factor score. All of those words go together to mean the same type of idea. The only difference is that the way that these things are talked about and their purposes sometimes obfuscate how they have these underlying commonalities. Because random effects are for handling dependency, whereas latent variables are for measuring unobserved constructs. So the way that the blocks fit together then, most research questions are phrased as an answer that needs a linear model. So is there an effect of a predictor? Is the effect of this predictor the same for everybody? Or would you have some kind of moderation in play? Is a predictor still significant after you control for some other stuff? Like those are the basic kinds of research questions that linear models almost always are brought in to answer. But then if you have anything other than the simplest case of an independent sample and a pseudo-normally distributed conditional outcome, you need something else. So that's where the other blocks come in. If you need to add to the model, we need some way of doing iterative estimation, such as through maximum likelihood, or by combining maximum likelihood with priors to create Bayesian estimation. The other blocks that we need then also are dictated by what kind of outcomes you have. For anything other than conditionally normal, you need link functions. And if you have multiple dimensions of sampling, beyond just one simple random sample, we need latent variables or random effects. So most designs in psychology, education, and basically all over the place would have more than one type of outcome per sampling unit. And so for the purposes of this, I'm thinking of people as what's being sampled repeatedly. So we might have people have multiple outcomes over multiple occasions, responses to multiple items, multiple trials, and all of that stuff. And what happens is that each dimension of sampling that you introduce then brings with it its own type of variability. So when I teach this stuff, for instance, this fall, I will start off at 12:30 teaching longitudinal models on Tuesdays and Thursdays. And with that hat on, the way that I'll talk about this is how we use random effects in longitudinal analyses, where the repeated observations are multiple occasions. And what we're trying to pull apart are the common sources of between-person differences. Why do some people start out higher? Why do some people change faster? That is an underlying commonality that goes through all of their observed occasions. What's left over then is within-person information. Why am I higher today than I was last time? Why am I deviating from my own growth trajectory? Those kinds of things. Then at 2 o'clock, I take that hat off, I put my SEM hat on, and I talk about the exact same thing with different words. Now we have repeated item responses as the multiple observations, and what we're trying to represent is between-person differences in the underlying trait that those items are thought to measure. And so now it's not a random effect, it's a latent variable. And we're trying to parse out what is in common across the measures as indicative of the trait from what is left over as residual item-specific error. But if you think about this, it's really kind of the same thing. It's interesting to me the way that it gets talked about differently because these models are used for different purposes. So random effects are for handling dependency. You want to be able to allow observations from the same sampling unit to have additional correlation because of that common sampling. And so, for instance, if I just had time within person, I might need at least one random effect, maybe more. If I had doubly nested designs like in education, we might need 2 layers of these random effects. And these models go by a lot of different names. I prefer the term multi-level. If you hear it from other people, they might say mixed effects or HLM for short. On the other hand, latent traits are for representing the idea of true score variance that is uncontaminated by measurement error. And that's a different purpose, but it's the same methodology. And here, the models for things, the names that we give them are tied to the type of response format. So if you're willing to believe that your item responses are conditionally normal, then we would say that we use latent variables in a confirmatory factor analysis framework or a structural equation modeling framework. If your outcomes are categorical, binary, ordinal, or nominal, otherwise known as polytomous in this context, then the latent variable models would go by the name of item response theory, IRT, or IFA, or item factor analysis. But it's all kind of the same idea. So to me, random effects and latent variables are mechanisms with which we can do a better job with the data that we have. It allows us to use all available data, to not delete whole people if they're missing part of the information, and it allows us to both quantify and then predict why it is we have all these different sources of variation. So what makes people different from each other, what makes occasions different from each other, what makes items different from each other. But I didn't always understand this as well as I hope I do now. So I want to tell you a brief story. Back in grad school, these are some people I went to school with at KU. This is Jim Bovaird, currently faculty at the University of Nebraska-Lincoln in Ed Psych, and Larry Locker, who's faculty at Georgia Southern. And we were hanging out after work on a Friday shooting pool, and Larry was really bummed because he had just had a paper rejected. Now, the world that Larry lived in is the world of psycholinguistics, which is a combination of linguistics and cognitive psychology. They are focused on how properties of words affect people's perception and performance with things related to language. And their types of research designs invariably involve an outcome of response time to stimuli that are either real words with various properties manipulated or fake words. And you have to decide whether it's a real word or a fake word. And within this type of design, everybody responds to the same items. And at the time, there were debates about what the best way was to analyze that type of repeated data. And he was telling us that the reason his manuscript got rejected was because his F1 ANOVA was significant, but his F2 ANOVA was not significant. And I'm sitting there going, okay, I know what ANOVA is, but what the hell's an F2 ANOVA? Like, I've never heard this before. Well, it turns out what he was talking about are different ways of aggregating data, not models, but aggregation strategies. So for instance, if I have an experimental design where I have manipulated 2 different features of an item, so I have got 4 possible combinations, and let's say that I've got 100 items of each type. One option to do an analysis is to aggregate items that are the same kind. So you would literally take your data, collapse it down to one mean per person per condition, and then stick those person means in a repeated measures analysis of variance. So that's the F1 ANOVA, where we keep all the person variation, but we eliminate all of the item variation of items that are supposed to be of the same kind. The other way of thinking about it is by thinking of persons as the nuisance and focusing on the items as the unit of analysis. And so in this strategy, for each item, they would aggregate over all the person responses. So you would have an item mean, and then those item means go into a regular between groups type of ANOVA. And at the time, both of these types of analyses had to converge onto the same answer for your results to be believed as trustable or generalizable across persons and items. And he's telling me this, and I started looking into this literature, and it's like, wait a minute. Sometimes we're throwing away person information, and sometimes we're throwing away item information. How can that be a good idea? And I wasn't the first person to question this. There's a long, contentious literature on this. And the point where Larry and I entered the story, what was happening in the journals was this F1 by F2 criterion, where they both had to be significant or your paper got rejected. So at the time, I was just starting to teach myself multi-level and mixed effects models by reading textbooks like Snyder's and Bosker. And I'm thinking of this like, well, aren't items nested in people? So can't this be a multi-level model? And I was all excited because then I thought, wait a minute, I've got it. We don't have to aggregate the data. I'll think of items as nested in people. So my level 1 model predicting the response time to each item for each person would have all the item characteristics in it. My level 2 model would have random effects for mean differences across people, maybe some random slopes if the design permits it. Then I don't have to aggregate the data. Then I can have any kind of predictors that I want, and they can be person things and they can be item things, and it's going to change the world. Only one problem. It's still wrong. What I recreated is the F1 ANOVA on all the data. Because in this analysis, the only source of random variation that I'm explicitly representing is across people. So I was thinking of it like this. I was thinking of it as between person versus within person, where we would need a random effect for people because some people are faster at this task than others, and then we have differences across items as part of the residual. But no, just as some people are better than other people at this task, some items are easier than other items within this task. So what I neglected to understand initially that I now have a better sense of is the need to separate out both stimulus dimensions and allow them to have random effects. So it becomes crossed at level 2, where what's left at level 1 is the person by item interaction. So after we control for which person it is and which item it is, why is it that some responses are higher or lower? We don't know, we just call that residual. So the full model would look something like this, where I have response time as my outcome per trial, per person, per item. So the T allows us to put in predictors at that lower level interaction term, such as, is this the first item that you've seen, or is this the 122nd? Because people may get better as time goes on because of practice, and they may also get worse because of fatigue or boredom. So trial order is likely something to matter. There may be other things that characterize individual trials that we might want to consider. But in his context, all he cared about were item characteristics, so we can put those in the model. And we have a random intercept for people here, this red U term. That allows some people to be faster than others. We have a random intercept for items that allows some items to be responded to faster than others. And critically, it allows remaining item differences among items that are ostensibly of the same kind. So all of that within condition variability that got thrown away is right here. And the correct way to think about the effects of an item predictor is, of all the reasons why some items are faster than others to respond to, how much of it is because of the things that you've got right here? Because leaving this out is a very bold statement that you have completely and fully explained all the reasons why items differ from each other, and even the best experimental design is probably not likely to do that. So it allows us then to include predictors of each of these kind, and we decided to publish a paper describing this approach, and we fit a data set that he got rejected from something else, so it wasn't going to be used for anything anyway. By the way, grad students, pro tip, if you have data that get rejected for its original purpose, try to find a home as the token example in a methods article. I've done that like 3 or 4 times. So that's the only way that my master's thesis got published, by the way, was the token example in an article that had nothing to do with the content of it. So we fit a model then, just initially without predictors, to try to decompose how much variability that was attributable to each source. And so this is sort of G-theory-like from what I understand in terms of being able to capture different reasons for variance. And what we found initially was not encouraging. 24% of the variance in response time had to do with who was providing the response. Only 11% had to do with which item it was. So if you think about the potential for these item predictors to predict response time, the best we could possibly do is 11%. Because item predictors can't tell me why some people are faster. Item predictors can't tell me why some trials are faster. And so we did a little demonstration where we had a significant interaction, and it looked like the F2 results were the closest to those provided by this crossed random effects model, as it stands to reason, because items was the source of variation that the predictors were focused on. So I did a simulation that was actually published in my longitudinal textbook because I have a chapter about these types of models, just to demonstrate that, yeah, if you're interested in testing person predictors, the person variance has to be in the model as a random effect. You can't throw the variance away, you can't ignore it. Likewise, if you're interested in testing item predictors, the item variance has to be in the model. And so it works out very neatly in those cases, and the same is true for random slopes. So then it got me thinking, well, am I always going to be wrong? Like, do we always need items as a random effect, or is it only sometimes? Well, there are some situations in which we don't have to worry about whether or not items need to be random, because the predictors and the fixed effects in the model have already addressed all potential item differences. So for instance, when would this happen? When you're fitting a measurement model. So in IRT or in CFA, each item gets its own set of fixed effects that describe its difficulty and its discrimination. So there's no remaining differences because each item gets its own set. There's no error term to that you would need to consider. Likewise, if you had features where you only had one item per unique combination, so in that 2x2 grid, if I only had 4 items, one of each kind, saying which of the 4 it is all I need to do. There's nothing else to be explained. Another instance, the type of data that I've worked with in people in cognition is multi-level analyses of naturally occurring kinds of items. So if I asked you, think of the best 10 memories from your childhood and tell me about them and answer these questions. Or if I'm tracking your eye movements to a scene, or if I'm tracking your speech in answer to a question. Each of these individual observations is clearly endogenous to the person. My first memory is not going to be your first memory, so we don't have to worry about this idea of common item variance in these situations. But what about if items are randomly generated? So one of the things that I was exposed to at KU was Susan Embrinson's work on matrix items and how she developed basically blueprints where there were certain dimensions by which the items could vary, and she could make items on the fly. She did not have to have an item pool because she could combine their features in novel ways to create items that met the targeted level of difficulty that she needed. And in that kind of design, I was thinking, well, if the items are unique for each person, then it's more like speech than it is, traditional test. But if the items are constructed with the same blueprint, then that kind of gets us back into the need to control for random item variation. So why this ultimately matters to me is because I was trying to meld my two worlds together and take what I had learned about cognition and attention and turn it into the goal of measurement of individual differences in those traits. So as I was preparing for comprehensive exams and doing reading, I became more and more aware of this sort of duality of research paradigms in psychology, where I was reading articles about visual attention where they might have 10 people, and those 10 people had to answer response time trials that are like thousands of them that varied in tiny little different ways to explore the architecture of cognition. Whereas on the other hand, there are articles trying to measure like executive function, and they might have a test that has 20 items, and everybody takes those same 20 items, and there's a lot more people. These are very different types of research designs. But where they start to meld together is in how people think about the data. So both of them have relatively, I don't want to say simplistic, but more straightforward ways of characterizing individual differences in performance. If I'm in cognition, I take the person's mean across trials and I think of that as my best estimate of their ability or their speed with this task. And I might do the same thing if I add items together and think of the scale score as my best estimate of someone's true latent trait. But we can also do better than that by switching over to Lego number 4, the inclusion of random effects / latent variables. And so rather than estimating, say, the mean across trials as my best estimate of ability, I could fit a random intercept instead, which is conceptually the same, but random intercepts don't have to have all the item responses, and they can adjust for differential reliability and differential variability within subjects. You can also fit what's known as random slopes. So in all of these cognitive studies, they are operating under the assumption that the manipulations are having the same effect in everybody. And there may be individual differences in the extent to which people are susceptible to the trickery that these sorts of experiments designed. Likewise, over in the psychometric land, we would fit latent trait types of models, so CFA or IRT or other types depending on the response format, And we can certainly have multidimensional assessment there as well. So I tried to combine these two worlds in my dissertation. And what I decided to focus on was visual attention, in particular in visual search. And just very briefly, since this audience probably doesn't care too much about that, the idea of attention is it's a filter on the world. So all of the information that your eyes perceive and that your ears hear does not get in. Attention is your process for filtering and selecting on that information. And that can happen internally in response to your goals at the time, like hopefully you're trying to attend to me as opposed to what your socks currently feel like inside your shoes. And now that I've said that, you're all thinking about your socks. Or it can be something that captures your attention, like a ball bouncing into the road. You know to stop your car because where there's a ball, there's a boy. So that would be like endogenous versus exogenous control. In the context of aging, though, there were basically no real good measures of attention for older adults, which is a shame because this is a population where deficits in attention really matter. You know, you can give someone glasses, you can give someone hearing aids, but you can't fix attention. And so being able to diagnose problems before they show up as real problems is a really important thing. So this is what I decided to focus on. The paradigm that I used to try and measure attention was within something that's known as change detection tasks. So these are the stimuli that I created. These are literally pictures taken from the front seat of my car. I made my then boyfriend drive me all around Kansas City, Topeka, and Lawrence, Kansas, taking these pictures, and I taught myself how to use Photoshop to make changes to them. So the way that it works is that each picture is shown for 280 milliseconds, separated by a gray blank screen that's shown for 80. And that gray screen essentially swamps out any local motion cues that would alert you to the change. And so you have to search through the picture slowly and carefully to find what it is. So here's one version of the picture, and here's another. What's the change? Yeah, the exit sign was removed in the second one. So these pictures varied in 4 different dimensions. One was just how cluttered the scene was, so how much stuff was in there, and this was rated by independent observers to get the stimuli values. Another was how relevant the change was to actually driving. So hopefully, if you don't want to be in the exit-only lane, you're paying attention to the fact that you need to change lanes. So that would be a change that a driver should notice right away. How bright the change was measured in terms of the pixels involved, and so that was more of a physical measure. And then whether or not the change was made to a legible sign. So I had 155 adults. I ended up keeping 46 of the items. And like the paradigm at the time that these pictures were being used in, my outcome was response time, but it was censored. Each trial, I allowed up to 45 seconds for someone to search through the picture, and if they didn't get it by then, it was counted as incorrect. So that was my cognitive hat, trying to figure out all of this stuff. Then we go to the measurement hat, and Susan Embertson's help with this. And at the time, I was like, well, I want to do a latent trait measurement model, so that means I need to do IRT. How do I fit response time into IRT? I know, I'll cut it up. I've learned better since then, but this is what I knew how to do in 2002. So after a considerable amount of preliminary analyses, I decided on these cut points to address the problem that there's this timeout condition as a potential. I now know that this could be a censored model instead, but that's neither here nor there. And as Susan does, I was interested in examining the extent to which I could predict item differences in difficulty with these design features that I introduced into the stimuli. So I fit what is known as an LLTM linear logistic test model. Linear latent.
Oh, no, logistic.
Yeah, it's like 1974. It's an older one. But the key idea is that rather than estimating a separate item difficulty, what you would estimate is a linear model to predict the difficulty. So now we're getting the Legos back in here. So I put in the 4 features, and I found that the difficulty that this linear predictor created was correlated about 0.6 with the actual difficulty if you just estimated it separately, and I was pretty happy with that. Then the real task then is to use this instrument, which used to be a task, but now I'm calling it an instrument, to try to predict outcomes that matter, such as driving impairment. So I had access to a very rudimentary driving simulator at the University of Kansas Medical Center, and I tested all 155 drivers myself. It was a 1978 Dodge with a CRT computer monitor on the hood, and the brakes and the gas and the steering wheel were all connected, and so it looked like they were driving like a 1985 video game. That's what it looked like. So it was very rudimentary, but it was free. And I was fortunate enough to get support from State Farm to pay for this project so that I could pay my subjects and hire some research assistants. So I was looking at the extent to which my measure could outperform existing measures in terms of predicting driving impairment as indicated by various measures of performance in this task. Interestingly, though, I also got access to most of their driving records, and I had self-report questionnaires as to whether or not they'd been in accidents. Absolutely nothing in my database predicted the probability of having been in an accident. Not age, not gender, not vision, nothing. But the task simulator turned out to be useful. What I did find was that my task uniquely predicted driving impairment above and beyond existing tasks, and I was happy about that. And then I did a follow-up study, which the generalized class just heard about this week, where I looked at the extent to which subsequent accidents could be predicted by these measures, and the driving simulator actually did predict that. So we did get a little bit of real-world validity there. So I was happy with this. I eventually ended up publishing it, but I learned a lot from doing this process. The first thing that I learned is that response time is really problematic as an outcome. So I was testing these subjects myself in a lot of the studies that I did in grad school, and they had a mouse, and they were supposed to click the mouse as soon as they saw the change. So if you ask the undergraduates to do this test right away. But what I watched my participants do who were older adults was look at it, watch it change a few more times to make sure they were correct, and then hit the mouse. So there's differences in decision criteria that are confounding the ability of visual search that I'm trying to measure. It's also not fair to ask people to click the mouse. So people who have functional disabilities may not be able to respond as quickly for reasons that are completely unrelated to their visual ability. It's a continuous distribution, so we have a lot of variability, but it's almost always skewed, so you have to figure out how to address that. And response time has very limited utility in real-world assessment. No one is going to be happy if their driver's license gets taken away because they didn't click the mouse fast enough. That's not going to fly. The change detection task that I had grown accustomed to using was also much less than ideal. Having other people rate the stimuli did not provide a way to create new items on the fly, or there's basically limited utility. I'd had to create brand new items for every time. The items were driving specific, and so that wouldn't necessarily generalize to other things. So what I decided to do for the next foray into this was use accuracy instead, and rather than measure response time as an outcome, I decided to manipulate it as presentation time as a way of introducing additional difficulty. And then rather than using the LLTM again, I decided to use legitimate explanatory item response models, as they are called. So let me tell you about this project and the models as well. So this was my collaborator on an R21 from NIH that paid for this project. This is Joan McDowell. At the time, she was the director of the Greyhawk Lab, as it was called. This is real. This is the KU Jayhawk from like the 1928, 29 or so. And she adopted this as her lab motto because she thought it looked like an old Jayhawk. So in her license plate said Greyhawk on it. It was a whole thing. So this is where the data were collected. And what we tried to do is design better measures of attention that were not photographs, that were things that were closer to what were being used in the studies, and to look at the dimensionality of ability under these measures. So we had 4 different ways of assessing visual search. 2 of them are the kinds of things that you would see in a traditional cognitive experiment. So for instance, on the left here, only one of the T's is sideways. Is the top of it on the right or the left? You have to find it as fast as you can. It's that one right here, so it's on the left. And so you would answer left or right. So it's a forced choice discrimination. On the right, only one of these H's, one of these letters is an H. Is it red or green? So again, forced choice. So these sorts of tasks are nice because there's a lot of things you can manipulate and control. They're not so nice when it comes for predicting ability in the real world. So we decided to make 2 tasks that would be more ecologically valid. Searching through a web page for information, so they had to find a target link of one of 2 places, and searching through your pantry to find food. So there's either a can of corn or a can of carrots in here, And in this case, the can of corn is right here. So we had these 4 tasks that were all being manipulated in similar ways, where the target location was, the amount of distracting information, and that kind of stuff. And the way that we decided to manipulate presentation time was through a linking design. Because you can't give the same presentation times to people of dramatically different abilities and expect all of them to work equally well. So what we did is link on a medium duration time, and these times were set by a lot of pilot testing ahead of time as to what would be useful for each. So everybody got the items under a medium duration presentation time. The younger adults also got items under a different, shorter presentation time, and the older adults got it under a longer one. So we linked on the middle. And we ended up with a fairly decent sample size out of this, and each person did 2 out of 3 test forms, 225 trials. So the first thing to fix then, since I'm used to thinking about response time as an outcome, is what do I do with accuracy? Well, I need a link function. So the problem with predicting accuracy directly with a linear model is that what you're actually trying to predict is the probability of a correct response, and probability is bounded by 0 and 1. So you would have to find a way to tell this linear slope, hey, can you shut off as you get close to 1, and can you shut off as you get close to 0? Turns out there is a way to do that. Some genius invented what we call the logit link function, or log odds as it's also known, which is the log of the odds of the probability of a 1. And through that, it creates a slope that when it's predicting logits is linear, but when you back translate that slope into predicted probabilities through what's known as an inverse link function, then your predicted probabilities stay in bounds. So that's the first way that this needs to fix. I also needed to swap out a Bernoulli distribution for the normal one. And then it's time to think about what the model should have in it. And so this is where the connections across the idea of random effects and latent variables really become quite salient. So one thing that I could do to predict accuracy in each of these tasks is fit what is known as a 1-parameter logistic model, or a Roche model to some people. And in this model, we have people as random and items as fixed. So I have predicting the probability of a 1, given a person's latent trait theta here, is a function of that minus item difficulty, where each item would have a separate difficulty estimate. So the notation doesn't convey this directly, but items are fixed and people are random. If I print it in terms of the logit prediction directly, then it looks more like this. Well, it turns out that this model is exactly the same thing as what I would call a generalized multi-level model with random effects. So I can still predict the logit of a correct response given theta, but now theta is a random intercept. So we switch the notation, but the idea is exactly the same. And rather than having this minus b, most software would allow you to estimate instead a linear model where you can shut off the general intercept and replace it with these item-specific dummy-coded variables. So it turns on as a 1 if it's that item and a 0 otherwise, which means the fixed effects then become the item-specific indices. Because they're being added together rather than subtracted, these are easinesses instead of difficulties, but you can easily flip the sign, and you would end up with the same thing. And the key idea here, though, is that because we have all items properties in the model with respect to either difficulty or easiness, there's no residual item variation that we have to worry about. It's full, it's saturated. If we then try to add the item features into the story, so the things that we were manipulating in these tasks, we can see how well they predict difficulty. So the LLTM would replace the per item difficulty fixed effects with a linear model that predicts them instead. So we would have, say, the amount of distracting information, the presentation time, and so forth. Well, if I write that same model as a generalized multi-level model, what jumps out to me immediately is that I'm missing something. This model does not have random item differences. There's no random effect for items. So I am assuming that this linear combination of the features of my items is going to perfectly capture difficulty for each item. And that's a very strong and testable assumption. So I don't want to do that. And it turns out after realizing this, I went back to my dissertation data and just looked at accuracy. And I looked at the results that I had reported from the LLTM versus the results that I would find doing the model correctly. And yeah, oops. The only effect that's still significant after you get the right standard error for it as a function of adding in that additional random item variance is whether the change was made to a legible sign. If it was more accurately detected. So live and learn, oops. So putting it all together, the idea of explanatory item response models intersecting with generalized multi-level models is a way that I can do all the things that I wanted to do at the same time. I can measure differences in ability across different people. That's my person random intercept right here. And I can add in person predictors, such as age or other types of features to describe why some people are better at this task than others. Likewise, I can predict why some items are easier than others with item features, and I can see how well I did by how much variance I've explained. And I can still examine trial level effects if I wanted to, as well as random slopes for how the effects of the item manipulations change differently. So I was excited about this, and I thought, well, this is, let's look at reliability, right? That's the next thing we do when you build an instrument. How well do the items work together? And it turns out really well in this case. So what I did was compute a test information function where the only item predictor that was in the model was presentation time, which was necessary for the linking design. And I converted test information into test reliability as information over information plus 1. And yeah, reliability is near ceiling all the way out until like maybe plus 3 standard deviations. So this is great, and 225 items is not very much by cognitive psychology standards, but it's a whole lot for the person who has to sit here and find the H or find the corn. And so the question is then, can we do this more efficiently? And so that spawned a third project, a sub-project of this, for which I had to ask a little bit of help. So that the key idea behind this is to basically turn it into a computer adaptive test. And I can do that so long as I'm working with random effects and latent variables as a way of indicating ability and not observed person means or sum scores. And I built what I refer to as the A team at the University of Nebraska with that guy and some grad students. And I got an internal grant to be able to collect new data. And what we were going to do is use the results of that previous study to generate a blueprint by which you could make new items on the fly. We were going to build an adaptive algorithm, and we were going to change the world. Well, it turned out that the item features that I had were very difficult to understand theoretically as to why they had the effects that they had. And I decided to eject from that plan and just use the items that we had and see if we could find a way to make an adaptive algorithm. And by we, I mean that guy. So I promised you that this was a recycled talk, and so we have some old pictures because when I put this together, baby Huey was about 6 months old. So Jonathan liked to look like Huey in several pictures and try and mimic him. So this is one of the better ones of here. I think he did a good job, don't you? I think this is pretty spot on. And this is just a little, little floor time. So by me, I mean him. He wrote a Visual Basic program to display the items, collect the responses. He wrote a Fortran algorithm that would estimate theta given pre-calibrated item characteristics and figure out which the next item should be. And the novel part of this is that we decided to increase or decrease presentation time as a way to fill in any gaps on the difficulty continuum. So it's kind of like we had new items on the fly, because if we make it displayed longer, it gets easier, and if we make it displayed shorter, it gets better. And since this is a new task, new slide, I decided to add some pictures today. So this is Ducky Momo, apparently.
Yeah, Ducky Momo.
Ducky Momo from, what is it?
Phineas and Ferb.
Phineas and Ferb.
He's your very best friend.
Yeah, they have matching Ducky Momo shirts, as well as matching Chiefs gear.
Oh, boy.
Go Chiefs. So how did we do then? So new data here to show you. After this adaptive algorithm, the top plots here are showing what happens to the standard error of the random intercept for person, otherwise known as theta, from these models. And it ends up around 0.3 across all these trials. But notably, it settles in about where it's going to be after about 15 trials. So all of this is kind of a waste. If we look at the trajectories of what the algorithm thought a person's ability was at each step and how it changed across steps, again, the change in ability settled into where it would be plus or minus 1 standard error after about 15 trials. So this is kind of amazing to think that you could speed up this process of assessment that much and not lose a whole lot of information. So these are for the older adults that we had. We had a relatively small sample. Then we collected data on undergraduates, and their standard errors were a little bit lower, but the same pattern happened. 15 trials is what it took. But a new phenomenon happened when I looked at the changes in ability. And if you've ever wondered what it looks like when an undergraduate has lost their will to live during your experiment, it's right there.
Don't care.
Yeah, don't care. I'm done. I'm done. I'm just going to keep hitting this until you make this thing stop playing. Can I have my psychology credits now, please? So this is actually a downside to the idea of having more reliable measurement by having more trials. And I broke out the data comparing what the mean ability was estimated at trial 50 for the undergrads versus trial 150. And they're actually lower. So I'm calling this the will to live effect, because the longer you go, the worse they get. So that was fun. It's an exciting set of possibilities that honestly we have not had time to pursue. I have moved further and further away from the world of cognition and aging and more into the world of methods. And so this has just been kind of a fun project that's been sitting on the burner. If anyone is interested, though, in helping us pick it back up, that would be a lovely thing to ponder. But the idea of all of these building blocks then shows up in terms of what reasonable next steps would be, in particular the idea of a link function. So these tasks are forced choice alternatives. So guessing rate is 50%. And none of my models had any kind of lower asymptote. So that might be something to consider. It turns out there's some identification issues when you combine Roche models with lower asymptotes that we hadn't counted on. But that's something to be solved down the road, as well as the potential for other sources of latent attributes. So the extent to which having more distracting information differentially impairs some people. That's multidimensional ability or random slopes from the perspective of multi-level models. So lots of fun things that we can consider. So that's all I have. Thank you for being here. I'm happy to take questions. Please.
Not to start in a bad way. I'm no, not bad at all. Apart from the pictures you picked for me. But
yeah,
that
let's go back to
now
that.
Now that I'm thoroughly embarrassed, I almost wore that shirt today, though.
Yes, Ducky Momo.
The thing that I'm struck by, you were modeling response time in 2006, but not accuracy. And in circa 2006, in educational measurement, we were all about what we call accuracy, correct responses. And response time, yes, that was on the topic sheet, and this was a topic back then as well. But shortly thereafter, there became a very large research literature on response times, modeling accuracy, response time at the same time. You still see that now. And what I wanted to get from you on your take from this is sort of your perspective on what you can learn when you step out of the silo of the discipline you're in. Like you were talking about cognition to begin with. This program's in education. What do you learn when you go across this? What have you and what is it that benefits you in that regard?
I would say that a flexibility is certainly a benefit, because when you see how people do things differently, it causes you to ask, well, why do we do it that way? And is there a good reason, or is that just what's been done? I did not have the framework in place in my head to understand that I could have a latent variable predict anything. Right, this outcome is problematic because not only is it response time and accuracy, but they're yoked together. Because if you time out on the task, you get it wrong, you don't have a time. So it's like the definition of missing not at random with respect to how these two variables play, and I didn't know how to do that. I now know that I can fit this as a censored outcome model in M+ and get latent traits for the original version that's not being cut up. But I think that response time as a primary way of measuring ability is problematic in a lot of contexts. And the cognitive folks aren't necessarily worried about measuring ability. What they're worried about is demonstrating people's, the changes in their performance as a function of very subtle manipulations. And so you can have a 6 millisecond difference be significant to them, and that meets their goals. But it doesn't meet the goals of measurement as well.
So, if I could follow up. Translating, would you say the following statement's true? That when it comes to models, math don't care.
That's right.
But when it comes to discipline, design is everything.
Design is everything. And being able to know, for instance, that I could have measured latent traits with any kind of outcome. Had I known that now, I probably would have done something even more different. Or for some people, a way to do adaptive modeling might be to start out with accuracy and then see how, like, once you have a sense of like where they're at, you could switch to response time or go back and forth in those sorts of ways. They may be complementary. But yeah, flexibility is everything, I think.
So if I could just summarize, for those of you who are in ed measurement, studying ed measurement is important because you need to know the context of what we're in, the world that we talk about. But stepping out of it and looking at the methods section of other people's studies is important too. And that's sort of where we're going for. Very successful people take methodology from one discipline and move it to another because it solves problems that hadn't been anticipated or haven't been solved yet through it. So
Yep.
anyway.
Yep. What
And
else?
thanks for the embarrassing picture.
Oh, yeah, my pleasure.
I didn't know they were in there. She warned me that she had some new pictures. That's
Yeah.
all I got.
We'll just look at the beach instead. How's that? What else? And by the way, these slides are on my website, and I am recording this. So assuming that the audio was captured correctly, I'll post the video next to the slides on my website later today. Zoomers? Yeah? Oh, there we go.
That was an excellent presentation. I learned a lot.
Thank you.
But there's still a lot I don't know.
Same.
More I know, more I think I know, the less I realize I actually do know. In educational measurement these days, there's a lot of talk and some work in having an examinee's experience be the experience of taking some set of items, where each examinee conceivably might have a different version of it using what's sometimes called automatic item generation.
Mm-hmm.
There really is not, to my knowledge, a methodology that's been developed to examine that. That's basically what's going on is that the testing companies are going to tell us they believe that the items are all comparable from a specific set of rules, and so we don't have to worry about that problem. And I guess I don't really believe that. Does what you're talking about potentially have any, give me any sense of a direction I might take to examine that issue?
Yeah, I think so. I mean, the question of whether or not they've controlled for everything that is responsible for an item's difficulty is an empirical question by seeing whether or not an item random effect contributes significantly to a model, or in a sizable way, not just statistical significance. Because what that represents is all the reasons you don't know about why some items were more difficult than others, and post hoc inspection of predicted random effects or deviations from that for certain items might lead you to figure out, wait a minute, we didn't control for this, or we accidentally confounded these two things, or there may be ways that the analysis of residuals could guide you towards a better blueprint. But yeah, I mean, I think in the cases of Larry's data, for instance, he only got 30% of all the reasons why the items were different from each other, but then when I showed him the results, he's like, oh, that's because I also matched on this, and this, and this. I'm like, why aren't those variables in the model? Oh, because I controlled for them experimentally. I don't need to control for them statistically. It's like, oh, yeah, you do. Like, that's where your power is going to come from. So I do think that to the extent that you're making an assumption about items being exchangeable, finding a way to at least check that assumption would be a reasonable thing to do.
Yeah, and how to do so will have design implications, obviously, what data get collected and what analyses get done. But I think that's a problem that those of us in measurement are going to be dealing with for, in a big-time way in the very near future, I think. I guess. Thank you.
Thank you for the question. Jihan?
So if we want to model the generalized linear mixed model as exploratory IRT, we model the item difficulty as a random effect,
Yes.
and we adding, say, item characteristics as a predictor.
Mhm.
So in IRT, I think the item difficulty is fixed effect, at least. So
Yes.
there is no residual because it's displayed itself.
Mhm.
And while we now have random effect, does that have same meaning with fixed effect? Because it seems that if we want to know each item's difficulty, we still need to get the information from that random effect component for each
Yes.
item. Yeah.
Yes, so if you wanted to get back to each item's difficulty, you'd have to add together their predicted difficulty given the linear model for their fixed effects plus their random effect. And actually, I have an example of one of these analyses, and it's almost spot on if you just estimate a Roche model versus if you break it into known and unknown pieces like that. One avenue that I haven't explored yet that I'm curious about is this idea that fundamentally these are Roche models, right? Explanatory item response models are super fancy and cool, but they're Roche models. We're assuming all these items are equally discriminating. And one might think that item features might control how discriminating an item is, right? Some of the features might matter more. And so that was something that just in terms of software, I didn't know how to do. And certainly these standard multi-level packages don't know how, I mean, that's not a built-in capability, but it certainly is a possibility in theory. And I know the latest iterations of M+ allow random factor loadings as a feature that this could be hacked. You could put a linear predictor on those as well. So that's, I think, an interesting area of future research.
Can I make a little comment about that? For the multi-level perspective, your mixed models, if I'm not wrong, you need a truly multivariate approach to incorporate other item characteristics. That is why the typical multi-level models, like in LME4, people do 1PL, because LME4 don't allow you to really do multivariate analysis in the sense of having multiple outcomes.
I haven't seen it described as multiple outcomes. I've seen it described as a heterogeneous variance model. And that sort of makes my head hurt to think about it, but it's like two random effects multiplying each other is the part that the stuff breaks down.
I will share a paper, I need to find it.
Okay,
That
good.
will go into that direction of multivariate.
Okay. What else? Anything from the Zoomers? They're all still here.
Yeah, they're still there, but the chat is quiet.
It is quiet, I saw that. That's because it's 3:30 on the last day of classes. Quiet is acceptable.
Thank you for being here.
Yes,
Thank you for everyone for
Let's
sharing.
speak a little bit.